have seen the approach of the computational plane approach, where we solve the equations not in the physical plane, that is x, y, z, but in a transformed plane, the computational plane, where it is expressed in terms of the coordinates are psi, eta and zeta. And so this transformation, this need for solving the equations in the computational plane also requires us to transform the equations which are described in x, y, z into the corresponding derivatives appearing in the psi, eta, zeta directions. So this transformation of equations is done systematically like the following. We will illustrate it with for a simple two-dimensional flow case. We will take the case of heat conduction. Let us say that we are looking at dou square T by dou x square plus dou square T by dou y square equal to Q xy. This is the equation that we have, where Q is a source term and T is the temperature, and of course there is a thermal conductivity and all that is included in this. Now when we are trying to solve this in a computational plane in 2 dimensions in terms of psi and eta, and our physical domain may be, for example, like this. This is x and this is y. This is transformed into the computational domain, and here if you say that this is A, B, C and D, this is A prime, B prime, C prime and D prime. Therefore there is this C prime, D prime corresponds to this, and this AB corresponds to this, A prime, D prime corresponds to this, and lines which are uniformly distributed here may correspond to lines which are curvilinear like that. Okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yes. So this is the physical plane and this is the computational plane, and we do not want to solve the equations in the physical plane because that is not a constant y line, but since this is mapped onto the computational plane like this, in which this is a constant eta line and this is a constant psi line, psi line here, therefore we can think of doing it like this. So now we have to write dou T by dou x. We can write in terms of this as dou T by dou psi plus dou T by dou eta, because x is a function of psi and eta in 2 dimensions, and this is psi x plus dou T by dou eta, eta x, and what we want is dou square T by dou T square, dou x square. So that is dou by dou x of dou T by dou x, and dou T by dou x is given by this. So this is dou by dou x of psi x dou T by dou psi plus eta x. Now we have to we can write this as plus psi x times dou by dou x of dou T by dou psi plus dou T by dou eta times dou by dou x of eta x plus eta x times dou by dou x of dou t by dou x. And each of these derivatives here, dou by dou x is like this, and that will have two components, this will have two components, and like that. So we have to evaluate this as dou t by dou psi times psi xx plus psi x times dou by dou x of dou t by dou psi. So this will be here we take this. So dou by dou x of something is equal to, so we can write this as psi x dou by dou psi plus eta x dou by dou eta of this t. So this is the operator which is acting on t, and now this is the same operator which will be acting on dou t by dou psi. So we can write this as psi x dou by dou psi of dou t by dou psi plus eta x dou by dou eta of dou t by dou psi, and here we have plus eta xx second derivative dou by dou eta, plus here again we have plus eta x times dou by dou x of this operator psi x dou by dou psi plus eta x dou by dou eta of dou eta dou t by dou eta. So we can see that this becomes dou square t by dou psi square. So we can write this as dou x square as psi xx dou t by dou psi, and here we have plus eta xx dou t by dou eta plus psi x whole square dou square t by dou psi square, and similarly we have eta x whole square dou square t by dou eta square. Then we have psi x eta x dou square t by dou eta dou psi, and then we also have psi x dou square t okay, so this is not there. So psi x eta x dou square t by dou psi dou eta here, so that we will have plus 2 psi x eta x dou square t by dou psi dou eta. So this is what we have for dou square t by dou x square, and similarly we will have dou square t by dou y square, we will have dou psi by dou y here and dou eta by dou y. So the operator here will become psi y dou t by dou psi plus eta y dou by dou eta of this. So we can write dou t by dou y equal to psi y dou by dou psi plus eta y dou by dou eta of t, and then we can again differentiate this, and finally we can get dou square t by dou y square equal to something similar, psi yy dou eta by dou t by dou psi plus eta yy dou t by dou eta plus psi y whole square dou square t by dou psi square plus eta y square dou square t by dou eta square plus 2 psi y eta y dou square t by okay. So, this equation q, which is x and y here, will now become q the corresponding psi and eta. So, we can put up this whole thing here as psi xx plus psi yy dou t by dou psi plus eta xx plus eta yy dou t by dou eta plus psi x square plus psi y square dou square t by dou psi square plus eta x square plus eta y square plus 2 of psi x eta x plus psi y eta y dou square t by dou psi this is the transformed equation from here, and one can see that in the transformed equations we have the matrix of the transformation. We have psi x, psi y, eta x, eta y, and double derivatives of psi and eta, these are all coming, and one can immediately see that this equation is much more complicated. There are many more terms that are coming here for the general case of transformation, where both x and y depend on psi and eta. Okay, in this particular case it looks like x direction there is no change, but y direction there is obviously change. So, some of the derivatives may cancel out, but in the general case all these things are present. Now, what is also important is that whereas this equation we have only normal derivatives, here we have cross derivative term which is coming here. So, and we have these terms, the first derivatives which are not there in this, but what is especially important is that we have the cross derivative term which comes here, and we have seen that if we were to use a central differencing scheme for, let us say that this point I comma j, then if we consistently use second order approximation, then the second derivative dou square t by dou eta dou psi will be represented as in terms of this point, this point, this point, and this point, and it will not have any contribution coming from this. So, this will be t I plus 1 j plus 1 okay, that let us put it as a plus b tau t I plus 1 j minus 1 plus c times t I minus 1 j plus 1 plus d times t I minus 1 j minus 1, this whole thing divided by some delta eta. This sort of approximation will come where a, b, c, d are some numerical coefficients, and especially what is important is that this discretization around point ij does not have any contribution from t I comma j. So, when we put this together in the form of overall, when we convert this into a t equal to b type of situation, the contribution to the central term, that is ij, from this derivative is 0, and there is contribution from off diagonal terms. So, a direct discretization of this will lead to loss of diagonal dominance. This is an important factor when we deal with this, and we have to deal with, we will have to therefore use a method which does not depend on diagonal dominance for the solution of this. For example, a direct method like Gaussian elimination, or an iterative method like conjugate gradient method. These are all methods which do not depend on diagonal dominance, but if you wanted to use Gauss-Seidel method for the solution of this, or even the TDMA method, they depend to some extent on diagonal dominance for assurance of convergence. So, there is a problem with this, and therefore, one way of solving this is to take this term onto the right hand side and evaluate all these things for the kth iteration in terms of k minus 1 based on the previous values. And since all these things t k minus 1 are known at all ij from the previous iteration, this will go to the right hand side. In the discretization here, you will have only terms which will be contributing to I comma j, and here we have normal derivatives appearing. So, and here we have something like the advection term also coming in this. So, this is the first derivative and this is the second derivative. So, if you were to look at it as some kind of generic scalar transport equation with advection and all that thing. So, there is a first derivative coming here. So, one has to do a proper stability analysis for a discretized scheme for this derivative and this derivative put together. So, that is another complexity that we have to deal with. And finally, what we also see is that there are derivatives, first derivative and second derivative of the grid coordinate transformation that is coming into picture, and for these things to be faithful to the original equation, we should have a smooth grid, okay, smoothness of the transformation. If the grid lines are smooth like this, then the second derivatives will be small, otherwise these will tend to dominate the whole solution, and you may get away from the diffusion type of solution that is expected for this. So, we would like to have this is an artificial thing that is being introduced into the equations because of the transformation. Okay. One can show that because of the transformation, the mathematical nature of this equation does not change. That is, if we are starting with an originally elliptic equation like this, then even this transformed equation will also be elliptic. If you are starting with a parabolic, then this will be parabolic. Okay, so that criterion is, that condition is maintained, that assurance is there that we are still dealing with the parabolic or elliptic equation as we started out with. Therefore, the well posedness or ill posedness is not affected, but there are transformation dependent terms which are coming here, first derivative square and then second derivatives. So the influence of these things should be suppressed wherever possible, and that is possible when we have a smooth grid. So if you have a discontinuous grid, so that you have discontinuous things where the second derivative becomes ill defined and all that kind of thing, then we have problems. And the most important problem is also with respect to the appearance of the cross derivative, and this cross derivative is multiplied by these metrics here, and the contribution of these metrics, these terms, will be higher if you have a non-orthogonal grid. So if the grid lines psi and eta are orthogonal and x and y are orthogonal, okay, for example, if these lines here are orthogonal with each other, then this term will be 0, identically 0, and it can be shown that way. But in the general case, we cannot expect orthogonality. For example, this is coming like this and this is here. So this is clearly not 90 degrees at this point, and this point here is not 90 degrees. So that means that for a general case of transformation, when you go from here to back to here, this transformation, the resulting grids are not necessarily orthogonal. If they are not orthogonal, then this term, this contribution here is not 0. We will have to live with cross derivatives, and these derivatives can be treated in this deferred correction mode. So we call this as deferred postponed correction. Because there is one term here which is being not evaluated at the current iteration but at the previous iteration value, the convergence of this scheme is compromised, is delayed, and the convergence, the correction which is coming after some time is going to delay it more if the value of the magnitude of the correction is large. So in cases where this term is large, that is where you have highly skewed grid. Okay, so if you have a skewed grid which is not orthogonal, then this term may dominate, and that may reduce the overall rate of convergence of an iterative solution of this with in a deferred correction mode. So these are some of the things that we will have to take into consideration when we are trying to solve the transformed equations in the computational plane. Now this particular form of the equation, where it is like this, where we have psi xx and eta xx and psi x like this, these are not very useful because we are trying to write approximations for these things, and typically our computational grid is very simple like this by design, and it is very easy to discretize this into equal spacing here and equal spacing here. So if you were to rewrite this not in terms of psi xx but in terms of x psi xi like this, then your x psi xi, so that is dou square x by dou psi square, can be written for example as x I plus 1 minus 2 xi plus xi minus 1 by 2 delta xi whole square, whereas psi xx, which is dou square xi by dou x square, will have to be written as psi j plus 1 minus 2 psi j plus psi j minus 1 by delta x square. In the computational plane, in the physical plane here, your delta x's and delta y's are changing all the time, but in the computational plane it is easy to take this rectangle and divide this into constant delta x and constant delta y. So this evaluation of this is much more simple than evaluation of this, and here you have uniform grids and here you have non-uniform grids. So the accuracies of the evaluation of this is also compromised. So making use of the relation between metrics expressed in terms of psi x and x psi, which we have derived earlier, we have shown that psi x, psi y, psi z zeta x, zeta y, zeta z can be expressed as y eta y psi, z psi, z eta, z zeta, which we expressed in terms of the Jacobian. So we can go from here to here or from here to here, and we are saying that it is easier to deal with dou x square by dou xi square rather than dou square xi by dou x square. So we make use of this relation to rewrite this in terms of psi like this. X eta square x chi square plus y psi square minus 2 Okay, so this is in this form. We see that x the matrix of the transformation in terms of dou x by dou xi and dou x by dou eta and dou y by dou xi, these are appearing, especially when we have a smooth grid, so that these first derivative terms will go to 0. I think here we have made the assumption that we have a smooth grid, and for a smooth grid this is equal to 0 and this is equal to 0, so that we can cancel out these terms and we have a simpler form of this. So the idea of the computational plane approach now is to solve this equation for a given relation between these lines and these lines. So we are trying to map the physical domain like this into this. So this is, for example, if you say that this is eta 1, eta 2, eta 3, eta 4 and eta 0. So this is corresponds to eta 0. On this line here, this is eta 1 is constant, this is eta 2 is constant, and eta 3 is constant like this, and these lines here correspond to psi 1, psi 2 and psi naught like this. So if we want to discretize this, we need to evaluate dou psi by dou eta, dou y by dou eta, and dou x by dou psi like this, and that comes from the transformation. And how do we get the information? We can say that, okay, we know this boundary, and one can say that this boundary and this boundary are mapped, and we know that this varies from say 0 to 1 and 0 to 1 like this. So we know what this line is, that is a horizontal line at eta equal to 1, and we know that eta equal to 1 corresponds to this line. So one, and since this is part of the boundary, we can potentially say that we can potentially evaluate the matrix corresponding to this, but we do not know these lines. Okay, so that is part of the grid generation. So the grid generation is, the objective of the grid generation is to find out all the interior points in the physical plane, given that the external boundaries here, this A, B, C, D, correspond to the computational plane where A prime of A prime, B prime, C prime, D prime, and subject to the condition that in the computational plane we have uniform grid spacing. So this point here is topologically the same as this point here. Topologically means that we have I equal to 0, let us say 1, 2, 3, 4, 5, and j equal to 1, 2, 3, 4, 5. So this is I equal to 2, j equal to 2, and this is also I equal to 2 and j equal to 2. So if you were to write this in terms of I and j, and similarly I and j here, this point is 2, 2, 2 comma 2, and this point is 2 comma 2. So the objective of the grid generation is to identify all the interior points for in the physical plane, given the interior points in the computational plane, and given the boundaries of the physical plane to map with the boundaries of the computational plane. So that is, and we have a number of grid generation methods by which we can find all the interior points, and one can even use the condition of smoothness in order to derive this interior point, so that we can cross out these terms here, and based on that we will be able to find all the interior points. So once we know the interior points, we can evaluate these x eta. For example, x eta for this point here is dou x by dou eta. So that means that this is x of this point minus x of this point divided by this distance. So that is, we can write this as at constant I here. So x, this is I equal to 1, 2, 3, 4, 5, and this is j equal to 1, 2, 3, 4, 5. So we are writing x eta at 2, 4. So, this is 2 4, and we can write this as x2 comma 5 minus x2 comma 3 divided by 2 delta eta, and delta eta is what we get from the computational plane, and x2 5 and x3 5 are known from the grid generation. So, from that, because we know all the xy of the interior points. So, once we know the interior points, we can evaluate the derivatives in this way and we put those things here. So, after the grid generation stage, once we have found all the interior points and once we have numerically evaluated all these derivatives for the general case, then we will have an equation with given coefficients, with coefficients based on the grid generation and all that. So, these coefficients will be constants, and we have a second order equation with constant coefficients, which we can then discretize as per the usual second order accuracy or fourth order accuracy as we wish, and then we can convert this into an equation like AT equal to B, and this AT equal to B can then be solved for t at psi and eta, and using those values we can then come back to t at this point. So, the approach in the computational plane is to first identify the mapping between the physical plane and the computational plane. The computational plane is such that it is rectangular in case of 2 dimensions, and in the case of third dimension the zeta dimension will also vary between, it is like a cube going from 0 to 1 and 0 to 1 and 0 to 1 in the 3 directions, and within this we can have uniform spacing of coordinates of constants of lines of constant psi, constant eta and constant zeta, so that you have small cubes of delta psi and delta eta and delta zeta depending on the number of grid points we have in this direction, and what we then say is that this line A prime B prime maps onto the physical plane, in the physical plane the line or the curve AB, and we have as many number of points here as number of points here. Then we try to identify where we want to have these 5 points here, and then we fix the points on this side and this side. This is already fixed, and based on our consideration of where we want to have the grid points, we can fix these points here. And similarly, the points on these things are fixed, and points on these are fixed, points on these are fixed. Now, once we identify the boundary points, then we have to get the interior points such that we have a smooth grid, and then these lines here map onto the constant psi and constant eta lines here. So, based on that we derive all the interior points, that is we find at every ij what is psi I eta j and what is xi yj. So, that for a given point ij in the computational plane and the physical plane, we get psi I eta j in the computational plane and xi yj in the physical plane. Based on that we can derive the matrix either like this or in this way, and once the matrix are derived we can substitute them into the transformed governing equations to come up with governing equations with coefficients which depend on the matrix of the transformation, these kind of transformations. So, at that point we have an equation of this kind, and j the determinant of the transformation is also evaluated as we have already seen in terms of the matrix, so that we now have an equation which has derivatives of the variable in terms of psi and eta and zeta, and for each of these derivatives we make finite difference approximations, and then this equation is converted into a discretized form. And for good measure, because we are getting extra terms in this, we will have to do a stability analysis to see that the discretization scheme that we have got is reasonable, and we also have to derive the stability conditions for this particular scheme with these coefficients that are coming here for the given transformation, and then based on that we finally select a suitable discretization scheme, and then using the discretization scheme we convert the transformed equations into AT equal to B. And depending on the structure of this A matrix, we may choose to use either a Gauss-Seidel method if, for example, the diagonal dominance is preserved. If it is not there, then we have to choose something else, some other method, or we have to treat this term as a deferred correction. We finally use a particular method, and then we solve this to get T as a function of at ij, and T at an ij is also T at psi I eta j, and it is also equal to T at xi yj. So this is the computational plane and this is the physical plane. So this is how we can get a solution in this approach, which calls for a fairly complicated approach for a complicated geometry. So that means that we have to first generate the grid knowing only the boundary transformation, and from the computed from the generated grid points, the internal points and the boundary points, we evaluate the metrics of the transformation, and we substitute the values of the metrics of the transformation in corresponding to each grid point, and then get a transformed equation in the computational plane, and then we choose a discretization and then come up with AT equal to B, and then we solve this and then finally get a solution. This kind of solution can be applied to any arbitrarily complicated geometry. If it is a completely two-dimensional problem, then it may be possible to generate a grid which is orthogonal. For example, if one uses the conformal mapping techniques, then one can come up with an orthogonal transformation, which will mean that the cross derivatives will not appear if the cross derivatives are not there in the original equation. But for a general three-dimensional case, it is not possible to ensure an orthogonal transformation, and so in such a case the cross derivative terms will appear and we have to deal with them. And it would be that grid generation transformation would be very easy if we had an analytical expression for the transformation, that is analytical expression for psi in terms of xyz or x in terms of psi eta zeta, like that. In the general case it is not possible. For example, if you are considering a case where even a rectangular domain with 3 tubes, and you have flow going in the outer species, outer things like this, and if you have another thing which is smaller. So in the general case like this, it may not be possible to have an orthogonal thing, but it is still possible to come up with a corresponding non-orthogonal body fitted grid. And this non-orthogonal body fitted grid is such that this is also a structured grid. structured grid in the sense that the structured grid has the points, okay, the grid points here are at intersection of constant coordinate lines. For example, this may be a constant eta line, this may be constant psi line like this. So all the grid points are located along constant intersections of constant psi and eta lines. That is what is known as structured grid. And for example, here every point here is at an intersection of constant psi line and constant eta line. This is also constant. Okay, so we are looking at this transformed line here. So the corresponding point between this and this is along this constant eta line and this constant psi line. So the grid points here are intersections of the family of lines of constant coordinate directions, and in such a case a cell here will have 4 faces in 2 dimensions, and in the case of 3 dimensions it will have 6 faces. And not only that, if you know that this is I comma j, you know the immediate left neighbor, that is I minus 1 j, and right neighbor I plus 1 j, and also the top one which is I j plus 1, and the bottom which is I j minus 1, and also the front and back. So in this particular case, in a structured grid, you know where you are with respect to the neighboring points, and that kind of structure is inherent in this. And this structured grid will preserve, for example, the diagonal structure of the A matrix in the that we would get for elliptic equations and so on. So the resulting AT equal to B based on the transformed equation will preserve the diagonality of okay, will still remain diagonal, although we have extra terms coming here. So structured grid is useful from the point of view of knowing the neighbors, which is important when we want to deal with higher order accurate approximations for the derivatives. If you want to have a third order accurate one sided differencing, you need to have 4 neighboring points. So that means that you must have I minus 1, I minus 2, I minus 3, and that kind of information is readily available in the case of structured grid. But in unstructured grid, that information is not available because these points are not along not at the intersection of these coordinate lines. So in terms of knowing the neighbors, that is an important aspect, and this also has possibility of structured coefficient matrix A, and we know that if you have a structured coefficient matrix, then the application of specialized methods like Gauss-Seidel method, okay, or the TDMA and the strong implicit procedure, these kind of methods are much easier with the structured coefficient matrix, and there is an advantage with this. And there are also modeling advantages in the case of a structured grid. For example, if you are looking at a flow domain like this and the flow is developing, then your velocity profile may be like this here, and then it may be finally going towards this, and this dimension may be typically, it may be some 5 centimeters, and this dimension may be something like 5 meters. So you have a very long and thin pipe. In a structured matrix, it is possible to make it into grids such that the aspect ratio, that is delta xy by delta y, can be large without affecting the overall accuracy of the solution too much. But if you have an unstructured grid and if you have a large aspect ratio, then the solution is going to be, accuracy of the solution is going to be compromised. So there are certain advantages for a structured method, structured grid, and that structured grid is actually carried forward, is used in this case of non-orthogonal body fitted grid approach to the solution of the governing equations, in which all the computations are done in the computational plane, and then the information is sent back to the physical plane. But this approach requires us to have a smooth grid, and then the fairly complicated transformations of the equations happens, and then addition of new terms, the cross derivatives, is a possibility. So there are certain things, advantages and disadvantages. But this approach is a generic 3-dimensional approach which has proved to be very successful in dealing with fairly complicated geometries. So in the next lecture we will look at an alternative viewpoint, alternative approach to the solution of equations, again on a physically complicated geometry.